Hi, today we're going to be talking about moments, center of mass, and centroids. Take this plank on a fulcrum. If we had a mass of m on this side and a mass on m on this side, and let's say they have a distance x from the fulcrum each, it's pretty obvious that the plank would be balanced, right? But let's say we had this mass to be 2m. What would happen is that this side would come down like this and this side would come up. And how would we balance it? Well, we find if we made this 2m, it would balance perfectly well. But also, if we doubled the distance from this mass to the fulcrum, it will also balance. So it seems that for this thing to rotate, it would be a quantity that included that considered the mass and the distance from the center, and we call this quantity moment. We're going to define the moment as mass times the distance from the fulcrum. That would be this change of x. I wrote it like this for a specific reason that you'll see later. Now, the concept of moments applies to more than just this example. It applies to any object who experiences a force field. With our example, we're experiencing a gravitational field going down. But the concept of moment extends to any situation. It doesn't just extend to the gravitational example. But for now, we're going to consider a downward force field. Okay? And so for this example, we should probably define what positive and negative moment means for this. If we set the right side to positive and negative, just as a starting base, what would happen if we had a positive moment? Well, that would mean we would have more tendency to move on this side. We know from just life experience that if you have more mass or more moment on this side, that it will go down on this side and then go up on this side. So it would have this motion. And we would say that this is a positive motion, right? Because it requires a positive net moment. Now, we can also say if we have more here, then it will move like this and like this. And so we could say that this motion would be negative. Now we can define these positive and negative motions past from just physical intuition and just see that we have our field going down, and whenever we have more moment on one side, that side will follow the field while the other side will not. It will go in the opposite direction. And so that's how we can generalize this past just what we've experienced. Make a general concept. So now we have a plank and fulcrum with various objects and perhaps various varying masses. And each mass is contributing to its own moment about the fulcrum. Now if we sum all these moments up, we get a quantity known as the net moment. And that net moment tells us how the plank will move in the end. If we have a positive net moment, then we get the positive movement, which would be like that. And if we have a negative net moment, we get a negative movement, which we discussed would be that. Now we're going to introduce a new concept called the center of mass. Now, for a center of mass, if you have this, let's say, set of all these objects, the center of mass is where you would put the fulcrum, and these objects would perfectly balance. Now what that would mean is that if you split this up like this, then the moment, the magnitude of the moment on this side and the magnitude of the moment on this side would be perfectly equal to each other. And because this side would be negative and this side would be positive, they would sum to zero. And zero moment would mean zero movement about the fulcrum. So we define the center of mass as where the center of mass, or the sum of the moments about the center of mass, is equal to 0. Now let's erase this. Let me draw something for you. Let's say we had varying masses on this number line, right? And let's say that the center of mass was right here, okay? And say the origin is right here. So now now let's consider this object. Let's say it has a mass mi, and it's xi away from the origin. Now we use the I just to signify that this is any of the elements. It's not special to one of these. We know that the distance between the center of mass and the xi is the change of x. That's what we're going to call it. Now we can say the moment about the center of mass is going to be equal to the mass in question times the change of x. Now we can rewrite this as mi xi minus the center of mass, and we in the end get that mi xi is going to be minus mi x center of mass is going to be equal to the moment about the center of mass for this particular object. Now we know from our definition of the center of mass that the sum of all these moments about the center of mass is going to be equal to 0. Thus we can write over here that the sum of the moments about the center of mass is going to be equal to 0. It's also going to be equal to the sum of all of these terms. And so now we can split the sum like this. And now because this is equal to 0, we can add this to the other side. And we're actually going to rewrite this as we're going to pull out the x center of mass out of the sum because it's a constant. And so this becomes the x center of mass times the sum of the individual masses is equal to the sum of the moments. That's what the moments about the origin is what this quantity would be. And so we can just rewrite that and say that the x center of mass is going to be equal to the sum of the moments about the origin over the sum of the masses. And we can also rewrite this a little simpler as the moments about the origin over the mass. So this is great for the center of mass in one dimension, if we just had a plank laying down. But we don't usually work with one dimension. How can we generalize this to 2 dimensions or 3 dimensions or 4 dimensions? How many dimensions we want? Well, let's consider our 2-dimensional plane here. And let's say that the x center of mass is right here. What that means is if we kind of let this x-axis fall and put our little fulcrum here, then it will perfectly balance at that point if we had various objects. And actually, let's put various objects here. And now what this means now is if we dropped all these objects on the x-center or the x-axis and we put our fulcrum here, then they will all balance on it. But now, what happens if we put our plank here, parallel to the x-axis, and we put our fulcrum on the center of mass and dropped all the objects on it? Well, it's still going to balance. It's not going to change just because we changed the y value. So what we realize now is that if we put our fulcrum anywhere on this line, then it doesn't matter. If we put the plank there, then the objects will still balance. Now, this generalizes also to the y-axis. Now, we defined our gravitational field as going down like this, and that this is positive and this is negative x-axis. Now, the y-axis, what would the gravitational field or any field be pointing to for the y-axis? It would be like this or like this. Well, we know that the positive values for y are up here and the negative values are up here. And we can see that the y-axis is just a 90-degree rotation of the x-axis, of like this. So it would follow that to get the field for the y-axis, we would just have to take our field for the x-axis and rotate it 90 degrees and find that they point like that. And so now the positive rotation would look like that, and the negative would look like that, or that. And so now we can just do the same thing. Let's say the y center of mass was right here. And we took a plank parallel to the y-axis and kind of put all the objects on one side. And we put our fulcrum here. We would find that it would balance in this field. It goes like that. And we, just like the x-axis, we know that this doesn't, the x value doesn't matter for the y center of mass. So all the possible places we could put our fulcrum for the y-axis would be, or the y center of mass would be on this line. Now we can see that these two lines intersect at a point. And at this point, if you put two planks and consider each one individually, the planks would both balance. And so this is what we would define as the center of mass of this system. It's the point where the moments about the y-axis and the moments about the x-axis are both zero. So finding the center of mass of a point mass system is great and all, but it doesn't really help us too much in our real world. We have shapes with continuous masses. So how can we find the center of mass for that? Well, it's not too hard. Let's consider a rectangle. And let's say this rectangle has continuous mass. Where would its center of mass be? Well, for the center of mass of shapes we call centroids, so that's what I'm going to be calling it for now. And let's consider the x center, the x coordinate of the centroid for this shape. Well, you can kind of consider this rectangle as a bunch of sections of smaller rectangles. Now, the increase of mass as you go along this line is proportional to the distance you move. What I mean by that is because these y values are always the same, the increase in the mass only depends on the increase, or doesn't only depend, but it's proportional to the increase in the x value. So as you go along here, you will increase the mass with a constant slope. And what this means is that to get to the halfway point, or to get to the point where the moment is 50%, or the magnitude of the moment is 50%, you simply just have to go halfway. And so the x center of mass is right there. And it's the same logic for y, except you're using intersections that go like that, and it's halfway in the y direction. And so the centroid of a rectangle is quite simple. It's just halfway between the x part of the rectangle and then halfway between the y part of the rectangle. So my phone ran out of storage, and so now it's like 20 minutes later. I lost all that footage. Great. But, so where we left off, we had a centroid of a rectangle, and that was great and all, but we're not just only going to deal with rectangles, we're going to have various shapes of various different sizes, and we're going to want to know how to find the centroids of those shapes. And so what we're going to do is we're actually going to find the centroid of the area between two curves. And why we should do this is because we can make that shape or that area into any shape we want, really. There's a lot of shapes we can make with the area between two curves. And so we're going to have curve f of x, and curve g down here. And we're going to consider the area between A and B. We're going to say that area is right here. Now we know the area can be written as this. B of f of x dx. Now, we're probably not going to know the mass of this object, right? Because it's just some random shape, and we're not really going to know the mass. What we're going to know is the density, usually. And we're going to assume that this is a continuous density, and we know that density is just mass over, well, usually volume, but in this case it would be area, and that's actually why we're using a sigma instead of a rho, because it's area density. And now a more useful way to write this would be differential mass, well, this should actually be a lowercase m, over differential area. Because we're going to actually find the integral of these. We're going to use integrals to find the centroids. And we're going to consider the differential rectangle right here. It's going to have a thickness of dx. And so this rectangle has a centroid right here. And let's say it has a centroid at some x value. That really shouldn't be a solid line. Sorry. And some y value. And so now we know we're going to have to find a point on the center of mass. We're going to have to find the net moment and the net mass. So let's focus on the net moment. And let's consider the moment of this rectangle here. Now, that seems like it's going to be a bit difficult because we have this whole area, this whole plane of mass, and we have to consider a moment of it. What exactly does that mean? Well, one property of the center of mass is that the center of mass can act, if you combine all the mass into the center of mass and make it a point mass at the center of mass, it will act exactly the same as the object as a whole. And why that is if you had, let's say you had a line here, and let's say the x center of mass is here, and you had your field going down like this. What the center of mass means is that everything, all the forces from here onwards, have the same effect on the object as all the forces from here onwards. So the effects of here and the effects of here negate each other. They sum to zero. And the only force that's left is the force that goes through the center of mass, the force that's not affected by, that's neither left or right. And so in a force field, the only force that needs to be considered is the force that goes through the center of mass. And because of that, we can just consider the object as the point mass. And so now we're going to consider the moment of the point mass centered at the center of mass, or at the center of mass, of each rectangle. Okay? Now, we're going to consider this as a differential moment. And we're going to find the differential moment about the x-axis. I'm going to label my axes here. And we're going to say that this is going to be equal to the differential mass times, and you might think we're going to use the x values, but we're actually going to be using the y values. Why the y values? Well, we're considering the moment about the x-axis. And let me draw the x-axis here again. And we're trying to find the moment about it. you can consider this line as like all the possible fulcrums that we could use. And to lay a plank down, we'd have to lay it like this. And it's going to move like in a third dimension, like this. And so, but you might notice that the distance from each fulcrum to whatever mass you're considering is actually going to be a y value instead of an x value. And so that's why we use y values when we consider the moment about the x-axis. And so now what would the differential mass be? Well, from here, you see that the differential mass is going to be sigma times dA. Alright? And this mass is still in the center, but we can still find the mass from the area as a whole. And so we can rewrite this as sigma y times dA. But what's dA? Well, it would be the differential portion of this integral. It would actually be this. And I'm just going to fit it in at the very end there. And so now we just need to rewrite the y, okay? Because we're going to integrate this in terms of f of x and g of x. And the y value is going to be the midpoint of this rectangle, or the height of this rectangle. And so that's actually going to be the midpoint between the f of x and g of x. And if you remember from geometry, the midpoint between 2 points is actually going to be the average between them. And so that's going to turn into f of x plus g of x over 2 times f of x minus g of x dx. So now we can just rewrite this as the differential mass, or we can integrate this. And if we integrate this side, we just get the moment about all the moments about the x-axis. And this is going to be equal to the integral from a to b. And we can pull out the sigma and the half, and we can multiply these two together, and we get f of x squared minus g of x squared dx. And so that's going to be our moment x. And I didn't write this down, but the center of mass is going to be equal to the moment over the mass. Forgot to write that down. And so we're just going to have to divide this by whatever the mass is. We know the mass from our definition here is going to be sigma times a, and we have a here. And so we can just say that the m, the mass, is going to be sigma times a b f of x minus g of x dx. And so if we divide this by this, we're actually going to get the y coordinate of center of mass. And it's for the same reason why we use the y values here. When we consider the moment about the x-axis, we're considering y values. And so obviously we're going to get a center of mass in terms of y's. And so we can, in the end, conclude that the y center of mass is going to be equal to these sigmas cancel, and the half comes out. And so this is going to look like this. So that's going to be our y coordinate for the center of mass. So we now found half of our answer. We're going to need now the x center of mass. And by the same token as the y center of mass, the x center of mass is going to be the moment about the y-axis over the mass. So the moment about the y-axis is going to be, or the differential moment about the y-axis is going to be differential mass times x. And so it's pretty much the same process. We stub in this sigma dA, and then we find dA. And so come here, say that the differential mass of y is going to be equal to sigma f of x minus g of x dx x, and now we integrate this, and so all that turns into is that the mass, the moment about y, is going to be a to b sigma f, x f of x minus g of x dx. And so now we just put this over this, the sigmas cancel out, and thus we get that the x center of mass is going to be equal to the integral from a to b of x f of x minus g of x dx over the integral from a to b of f of x minus g of x dx. And so that those two are the coordinates of the center of mass, or the centroid of the area between two curves.